So yeah, then let us just continue. How is it working with the practicals? How far are you now?
We've done all the parabolas.
Yes.
So now they need to open it.
Yes, yes, of course. So you know you have now the XY positions, and these XY positions you are putting in Excel, and then you are making the best fit line through. So and then you are getting a function, yeah? So and with this function, then you have to calculate the standard derivation and the error, yeah? But there is somewhere in Excel a function where you have just to click on it and then you are getting it. So and then you should compare a source material which has a lower density, how it looks like then, and with source material you use it with a higher density, how it works with that. So for the ES303 you are doing this to explain general physical properties, you know, general physical properties, and those one we have done in class, yeah. Using Stokes' law and these things. So, and for the ES301 report, you should write it down in respect to natural hazards. Yeah. So, and then we are done with this. Now we are continuing here with Hawaii. So we have actually in Hawaii two families of ocean island basalts. So we have two families of ocean island basalts. Hawaii, two families of oil. So and therefore we have now to explain what two types of families you have. Therefore we are making another nice diagram. Looks like this. And maybe you remember from ES303, have you done the basalt tetrahedron with them? Or already? So, but we will do it again. So, but if you are watching at this basalt tetrahedron, then you can, then you will discover three different planes. And on every corner of these three different planes, you have other minerals. So, and that is just the basalt tetrahedron in 2D. I just flipped it on a 2D surface. So now we have their different minerals. So, and therefore we have here the mineral quartz. So the quartz, of course, does only occur in silica-saturated rocks. If we are talking about two families, and we have here quartz inside, then we have one time a quartz bearing rock, and the other time it is maybe not a quartz bearing rock. So and therefore I'm putting here the mineral nepheline. Nepheline occurs in the QAPF diagram on the bottom side, because it is a fluid mineral where quartz is on top. Yeah? So then we are putting here the mineral diopside. Then we are putting here the mineral olivine. And then we are putting here the mineral hyperstein, and the hyperstein, that is an OPX. and therefore I'm writing here just the Endstatite. No, we are writing here OPX, and here we are writing instead of dioxide, we are writing CPX. So, and now I will show you where are the two families are located. So, and then I'm putting in this field. Then we are putting here inside another field, something like this. So, and then we have a third field. Something like this here. So then here we have the alkali, olivine, basalt. That is this one here. So then this one here in the middle, that is just for comparison, that is the Middle Ocean rich basalt. And this one here, these are then the tolleites. So, and I told you last week, when we are looking at the Hawaiian volcanoes, I mean we have there seven, the whole Hawaii chain consists of 7 volcanoes. So, and the youngest one, I mean the first ones, they are tolleitic, and later on they are then alkali olivine basalts. So in there I told you also we have at first the tolleites, then we have the alkali olivine basalts, and then in a very late stage we have this nephelinite. And the nephelinite is even much more silica undersaturated compared to the alkali olivine basalt. So that means if we are looking in a magma chamber, in the shape of a magma chamber, like we have it here, so then we have in the upper part, we have at first the tolleites, and then the alkali olivine basalts. So that is the differentiation what we have at OIP. What is going on here? Sue, are you looking for us? He is there. So, that means the youngest volcanoes are tolleites, later alkali olivine basalts. So, and lastly, nephelinites. So now we have to look at how it looks like in the field. We need our model for oil. What we have at first, we are making at first again the oceanic crust. So why do you think I'm making here this stent? Do you have an idea why I make here this stent? So if you are making a tent, what you are doing when you are making a tent? You need some weight on it, yeah? You need some weight. So when we are forming a volcanic island, like here in Viti Levu, yeah, you remember from the ES301 field trip, we have here everywhere this volcanic necks, yeah. So when there is a sign, I mean that is, and you have basalts, of course, I mean there's no discussion. So but I mean the highest mountain here in the Viti Levu, there is Mount Naukasi, is it? No. Mount Victoria. So and this mountain is 1,300 meter high. Yeah, it's 1,300 meter above the moor level. Yeah, so that means that it's a huge weight. Yeah, so and if you are putting some weight on something, then you are producing a dent in the oceanic crust. So, for example, that is now Mount Victoria. So, and that is the mountain. Here we have again the ocean. So, and then we are going now down into the Earth's mantle. Then we have the boundary in about 650 kilometer step, 650 to 700 kilometer step. We have the boundary between the lithosphere and the asthenosphere. So we have no boundary between the lithosphere and the asthenosphere. We have the boundary between the upper mantle and the lower mantle. Sorry for that. That is then here, then we have this upwelling here. We have here an upwelling at the boundary because there are the plums are coming from. I told you these, these plums which are responsible for the formation of oceanic island basalts, they are enriched compared to more in the pattern of the rare earth elements. So, and also the potassium group elements. And therefore, I told you just last week that there is this plumb component, and we have to think about the model, where does the plumb component come from? So, and there we discovered there could be an influx from the lower mantle into the upper mantle, but much more possible is that there are remnants of old oceanic crust lying around. So that is now the plumb component, and here you have your plumb. So that is the example for Hawaii. So, but now Lin is working on these rock samples from Coral, and there the potassium group elements are very depleted. So what means this then? That means here, just beneath our feet in a depth of 650 kilometers, there's not only any sign for an old slag hanging around. Because otherwise you will get these enriched components. Yeah? So but these samples, they are very chromium and very nickel rich, and cobalt is also a lot inside. Yeah? Yes. So and that means that is a pure mantle melt. What you are seeing in coral, that is a pure mantle melt. And of course, this is also reflected in the mantle xenolites, yeah? Because these mantle xenolites have a residual product from basalts. I told you this, the olivine is sinking to the ground, all the pyroxene is sinking to the ground, and the basalts are swimming at the top. So then we have this here, and that is the plumb component. Very heterogeneous. Due to the weight of the Iceland, the lithosphere as a dent. So yeah, I can remove this, yeah. So then we have making a small summary here. Here the oil. So and then we have the tolerators. So in these tolerators they are olivine, hypersteam, quartz, normative. And these tolerators are forming shield volcanoes. Hey, we are coming next week on Tuesday or Wednesday. Yeah? I need to do it this week. So when these tolerators forming shield volcanoes. So then we have later the alkali basalts. And the alkali basalts, they are nepheline and olivine, normative rocks. So and now you actually you must have a question. I have written here in the first line olivine and quartz. So you can have a tolite which is olivine, has olivine, or you can have a tolite which has quartz. But you can never have a tolite which has olivine and quartz. It's just not possible, yeah? Because olivine and quartz going not together. And that is because if you are adding to the olivine, to the Mg4 Mg2 SiO4, if you are adding one silica, then you are getting what? Then you are getting an OPX, and the hypersteam is an OPX. And if you are going back to ES303, or not only to ES303, just here a few weeks ago, then you are sitting at a peritecticum in your phase diagram. And that is the phase diagram which is spanned between olivine, that means forsterite, and quartz. So then we are going to the potassium group elements. So the potassium group elements like barium, strontium, rubidium are enriched compared compared to mol. So, and that is because of all these old remnants lying around. But alkali basalt is even more enriched as toluene basalt. So whereas the alkali basalt, Moment, so when the toluenes and the alkali basalts are from the same reservoir, but I mean from the mantle plume. So, but toluenes have a higher melt grade. That means if they have a higher melt grade, then they are depleted. So in the alkali basalt have compared to them a lower melt grade. Therefore, they are enriched. So, and if they are enriched, that means they are enriched in incompatible elements, like the potassium group elements. Because the melt remains longer in the magma chamber, that's all. So in all the incompatible elements, they are remaining as long as incompatible as possible. Yeah? So if a melt has a higher melt degree, then it has just a higher melt degree because it is more hot. So when we have the plum is stationär. And the lithosphere above is moving. The magma chamber within the lithosphere get neodymium and strontium isotope ratios as mol. So this was now what I have to say to the oils. So, but now we are looking for the next type of basalt. And there we are looking now for the continental flat basalt. The continental flat basalt. So the continental flat basalts, the shortcut for the continental flat basalts, these are the CFB, for continental flat basalt. So and these are single streams are up to 100 meter long. So then they have the biggest volumina largest voluminas are up to, or not up to, are moving with the R, making here a double dot. So when they are up to 10 kilometers thick, and can cover an area of 10 powered by 6 square kilometers. So that is actually wrong. They are not up to 10 kilometers thick, they are up to 1 kilometer thick. So because the highest mountains on this planet, that is Mount it is Mount Everest, and it is 8 kilometers thick. But now you have to think about why I wrote here up to 10 kilometers thick, and telling you that Mount Everest is only 8.8 kilometer high. So because we can add here again the 0, because I mean the 10 kilometer of this flat basalt does not show out completely out of the ground, yeah? So maybe there are 9 kilometers of that in deep. Lake Superior that is in Canada is even 12 kilometer thick. They were formed in a time scale of smaller than 10 power 6 million years. So that is relatively short. So in examples, that is, for example, the Panama flat basalt. In South America, and the Ethendeca in Namibia. So in both of them are formed 120 million years ago. So and therefore the Panama flat basalt and the Ethendeca, we will do an example and another example for continental flat basalt, which I will show you. That is then the one which formed Réunion and the Deccan trap in India. So, but at first we are looking, comparing them with more, and therefore we are checking the incompatible elements and the competent elements. Competent elements are up to 10 times enriched compared to more. So now we are going the incompatible elements. Are up to 50 times enriched compared to more. So now we have to think about why this is. Do you have an idea why the incompatible elements are enriched? So for example, now we are going to an extreme. The incompatible elements in a rhyolite are up to 1,000 times enriched compared to a basalt. So now we have to think about why this is. And therefore, I will give you now the first model. The first model from the Panama flat basalt and the Etedeca in Namibia. So first of all, we have to, and I told you just before, that the Panama flat basalt and the Etedeca is, both of them, they are 120 million years old, yeah? 120 million years. So, and you know in Panama flat basalt that is in South America, and the Etedeca in Namibia is the Etedeca in Namibia that is in Southern Africa. So, and both of them are 120 million years old. So, and now the question is why they have the same age, yeah? And what was the situation of the continent-continent constellation 120 million years ago? Where was 120 million years ago? Where did we have South America and where was Africa? Under 20 million years ago, there was South America and Africa were together. So, and then that looks then like this. So, with a little bit fantasy, that is South America, yeah? So, and then we have here Southern Africa, something like this, yeah? That is Southern Africa. So then we have to check where we have the Panama flat basalt. Somewhere here. That is 120 million years old. So, and then we have the Etedeca here. That is also 120 million years old. So, and here we have another guy, something like this. That is the cacao belt. That is 200 million years. So and now we have again to think about, first of all, why these continental flat basalts are so strongly enriched in incompatible elements. That is the first thing what we have to think about. And the second thing what we have to think about, what happens geotectonic wise 120 million years ago. So first of all, the continental flat basalts are enriched 50 times, they are 50 times enriched in incompatible elements. So, and where does this incompatible elements come from, which you can find in the continental flat basalt? So, where does the continental flat basalt go through, and the oil and the water does that not? As it says, it is a continental flat basalt, and therefore the basalt goes through the continental lithosphere. So, in the continental lithosphere is much more enriched in incompatible elements compared to the oceanic lithosphere. So, and therefore, because this belt is going through the continental crust, and therefore you are getting the contamination with the continental crust, and therefore the continental flat basalt is enriched compared to the oil and the water, yeah, in incompatible elements. You got this, yeah? So, and now we are going to the geotectonic thing. What happens 120 million years ago at this place? That was the opening of the South Atlantic. So, but now we have to prove, I mean, that one can see very easily that South America and Africa was one time together, yeah? And I mean, you can also use the fossils, yeah? You will find the same dinosaur bones in South America as in Southern Africa. From those dinosaurs which are 120 million years old or older, yeah? The younger ones you will not find. The younger ones which you find you will find in Jurassic Park, and this was the T-Rex, and the T-Rex the T-Rex was at 120 million years old there. There were some other guys there. I think the Stegosaurus were there, but I'm not sure. Yeah. Therefore, if you would like to know more about dinosaurs, you have to talk to Eleanor, yeah? But anyway, we are doing this here, we are not looking now here for dinosaur bones, we are looking here now for evidence from the basalts to prove if these two melts are coming from the same source, yeah? And therefore, you are using the chemistry. And there is an interesting line. There is this line here. So in the both basalts, they are showing chemically they are the basalts from the north are different compared from them to the south. So but both basalts showing this on both continental flat basalt region here and here, yeah? So we have here in the north, we have high PT. So and that means you have a high concentration of phosphor and titanium. So and here we are in the south, we have LPT. That is then a low concentration in phosphor. We are making in phosphor and titanium. So now we have to think about what for a meaning has the phosphor and the titanium regarding to a magma chamber. So therefore you have now to go a few weeks back when we did the CIPW law. So if we have a melt, if we have this melt regarding the CIPW law, then you are crystallizing very early the apatite, and the apatite contains phosphor, and then after the apatite you are removing the titanium. So and then you have just a fractionation in your magma chamber. So in that way you can follow up in this sequence. So and you have also the boundary goes straight through. So the boundary, this boundary that shows just straight through, and we have also a N depletion. In the mantle, no, not in the mantle, in the magma chamber. So what happens to the anorthite in a silica undersaturated magma chamber? It is just swimming to the top. It's floating up. So then flat basalts are related to rift zones. So, and I mean, here we have a huge rift zone because there we have the mid-oceanic ridge. So that was then the driving force, and therefore by driving you have settled at the beginning these two flat basalts. One is in South America, one is in Southern Africa, but both are chemically the same, and you can also see this on this high phosphor and low phosphor titanium line, which indicates even more that you have already fractionation in the magma chamber. So now we are going to the next example. The next example, that is then the Deccan Trap in India. So that is now India, something like this. Even more like this. Here we have a fault. Yeah, something like this here. So that is now the Deccan Trap. That is the India. So and here we have a small island. That is Réunion. So and the hotspot is nowadays beneath Réunion. So that means the hotspot is was moving from here to here, and that takes 0.5 million years. So the hotspot the hotspot from the Deccan Trap is today beneath Réunion. So, but if you are looking now at the basalts which you can collect here in the Deccan Trap and the basalts beneath Réunion, which one you think, which one basalt is more enriched compared to the other one, and why? So which of the two basalts or the two belts went through the continental crust? The one here or the one here? Yes, that is the one from India, yeah, because that is continental crust. So and the one which is which formed Réunion, that went only through the oceanic crust. So therefore, the basalt which you can connect and take is chemically or incompatible element, and which compared to those which formed Réunion. So yeah, how many times we have left? What? How many times we have left for class? What? 3 weeks. Yes, then we are actually done for today.